Good morning. Hello, good morning, recording in progress. We are at the seminars of the Centro de Astrobiología, and today we will have Marc Balcells. He's the director of the Isaac Newton Group of Telescopes. Later, we will see all this. I will just make a very brief personal introduction to him. I met him for the first time in year 2000. And after 15 seconds, I realized of two things. He was from Catalonia because he has a strong accent, and he has been sometime for a long time in the US because he has also a very strong American accent, I would say. Now, maybe it is British. He told me that he did his thesis in Madison, Wisconsin. And at that time, I know that he had been in the Netherlands because all the first year students at the Instituto de Astrofísica de Canarias, where he was a research investigator, know all the potential PhD supervisors. And then we, the youngers, know that he was a famous astronomer coming from the Netherlands to the AEC. Then our roads were in parallel. He was doing his stuff on galaxies that he will be describing just now. And at some time in 2006, I worked at the Isaac Newton Group of Telescopes. At that time, you were not the director yet, but just after I left, you were the boss. So for 1 or 2 years, you were not my boss. Now, since then, how many years have you been already the director of this?
Since 2009.
Since 2009. So I would say he's home now, and then he's going to show us his home. Thank you very much, Marc.
Thanks. Do I have to switch this? Is this on? Good. Good morning, everyone. Thanks for coming. I'm going to give a talk about the Isaac Newton Group in general. My talk is about recent developments, instrumental developments especially, but I've been asked if I could give a bit of an introduction to what is this observatory about, for the benefit of those of you who are not astronomers. Those who are astronomers have been at that observatory many times. Many of them here have been there many times. It's almost their second home. They did their thesis there. And not only that, but their supervisors did their thesis there too. The observatory in the Roque de los Muchachos in the island of La Palma is a fundamental center for observational astronomy in Spain and in Europe. It was set up in the 80s, in the 1980s. So as an observatory, it will soon have its 50 years. It's like around 40 years of age. It has now 14 telescopes, active research telescopes, working on optical light, infrared light, and then and now recently with the addition of telescopes that detect gamma rays using the Cherenkov effect on the atmosphere. They detect optical light, but they detect actually gamma rays. As I said, is a power home for optical astronomy. And I really, for those of you who are scientists who work in astrobiology, but you're not astronomers, I do encourage you to find the opportunity to visit the observatory. It's a good learning experience. and it's a beautiful place, and it's where most of your colleagues do their research at night. So this is the introduction. Let me see if I can operate this. So I'm talking about MOS. MOS is a short term for multi-object spectroscopy. So spectroscopy, everybody knows what a spectroscopy is, but multi-object spectroscopy is a key in astronomy to talk about instrumentation that allows you to target not just one star or one galaxy, but many at the same time. So thereby increasing the flexibility and the effectiveness and the efficiency of the observing. For the last 12 years, we've been building a massive new multi-object spectrograph. This instrument has been starting to take data now in the last few months. And that's the main topic of my presentation today. I will also mention at the end a development of another spectrograph of a different nature is also being built now, not by us directly, but by a collaborating institute. And is going to be installed in one of our telescopes and has specific application for some of the science that is being done here, because it's a spectrograph that's specifically tailored to study, to detect and characterize extrasolar planets. So, multi-object spectrographs, there are many in telescopes around the world, and starting by telescopes on La Palma, EMIR, Megara, are two instruments that are on the GTC on La Palma. But then there are many other instruments, each having their own characteristics, including, of course, NIRSPEC. There's a good connection here at this institute. So what does WEAV, which is our spectrograph, what is this particularity of WEAV? The main characteristics are that it has a velocity resolution that is high compared to what most other telescopes have. And that means that you see how the resolution, I refer to it as kilometers per second, because we use the Doppler effect to measure velocities of stars and galaxies. And higher spectral resolution means smaller velocity errors. So this is the characteristics of our instrument. In low resolution, we get velocity resolutions around 3 kilometers per second, which is an improvement respect to previous instruments. It has a multiplex around of 1,000. Multiplex is the number of stars that simultaneously can be analyzed. We will do 1,000 stars at a time. Then it has an IFU. IFU, this is an acronym for Integral Field Unit. This is a mode in which we acquire spectroscopic information, not for separate targets, but for a source that is extended in space. I will show examples specifically about IFUs, about integral field units. And then finally, the instrument is being designed with a pipeline, an analysis tool that gives you science-ready data from the beginning. And that's quite important for the scientists, because it means less investment of time in processing the instrument. Well, what is a fiber multi-object spectrograph? So what you do is you place a number of fibers on the focal plane. In this case, you put fibers in a square matrix. Each of the fibers takes the light into a pseudo slit and goes into the spectrograph. So you get information, the spectral information for all of the points in your extended object, in this case, a galaxy. The analysis is done from the pseudo slit to a standard optical design for a spectrograph, which you need to collimate the light, make it go through a dispersive prism or a grating, and then a camera to focus the dispersed light into the detector. WIF has 3 inputs so that you can feed the fibers in 3 different modes. Here the movie is showing one of the modes, is the multi-object mode, in which 2 robots grabbed optical fibers and place them on a metal surface. They stay there with a magnet, by a magnet. There's a prism, light is shines on them, and the fibers take the light into the spectrograph. Then there is a large integral field unit in which all 547 fibers are all packed into an hexagonal pattern, which you can see. Let me see. You can see it here, this hexagonal pattern. And all of these 500 fibers then send the light to the spectrograph. And finally, there's a mode called mini IFUs, in which we have integral field units, but small ones. There are 20 of them. This way, you can analyze, take, for example, a number of dwarf galaxies in a cluster and get not only the light from one piece of information on the stars, on that dwarf galaxy, but information about the spatial distribution of their properties. And well, a data system that delivers the light. What is a spectrograph? The spectrograph is a massive. This structure is 2.5 meters by 1.5 meter. It's sitting on a Naismith platform. Naismith platform is a platform on the side of alt-azimuth telescopes that remains gravity invariant as the telescope moves around. The main element of the multi-object spectrograph, however, is the fiber positioner. Here you will see, here's a telescope, down here is the primary mirror. This is the main ring at the prime focus. This is an optical corrector that is inside this black cylinder. And then on top of this, this is a cube of 1.8 meters of a side, weighing 1.5 tons. And this contains the fiber positioner. This element needs to ensure that the fibers are positioned with an accuracy of, with positional errors of less than 20 micron. So there's a tremendous work implied in the design and construction of this instrument, because you have to bring mechanical engineers, optical engineers, and then control engineers to ensure that in the end those fibers will be placed with an accuracy of 20 micron. Otherwise, your star will be there nearby, but the light, half of the light will fall outside of the fiber. And then you lose, then all your work is lost, because you don't manage to observe the faint sources that you are interested in. So the way this was conceived is a structure that was first installed in a telescope in Australia, and we have kind of replicated it. It has what is called a tumbler, and it has 2 optical plates. So you would have your instrument has the 2 optical plates, and this one here, the one below, looks towards the sky, because it looks towards the primary mirror, which is below. And so it receives the light from the sky. The one on top is where the robots work to position your fibers. It takes about an hour to position 1,000 fibers. So while you are exposing this side, you're positioning the fibers on the top side. And after the exposure is done, then you tumble 180 degrees. Start observing here. And then the robots will start positioning the next set of fibers. This is the way the instrument is conceived. And this is a plate with, in this case, 500 fibers of a recent test that we've done. You can see it's quite messy. The fibers cross each other. So you need to really know what you have done so that you can undo it afterwards in the right order. And I'm not sure you can see that because there's too much light, ambient light, but I wanted to show you what the large integral field unit is. It's actually a very small component here of this plot, is this circle here. This is the large integral field unit. From here, this is where this hexagonal of 500 fibers is placed. And we observe with this, we have these two positions, 0, 180 degrees. When you put it at 90 degrees, then the integral field unit is the one that receives the light from the primary mirror. Yeah, thanks. Better, a bit darker. I'm going to spend a little time on this integral field unit because it's the one for which we have obtained data, science data already. It is patterned as an hexagonal distribution of these 500 fibers, plus then a number of groups of fibers on the sides that I use to measure the brightness of the night sky. When you observe your target, your star, your galaxy, in addition to the light from the galaxy, you get the light from the atmosphere, which also emits light. I need to subtract this light. So you measure it on these fibers on the side. And well, first light observations, we are observing, we started commissioning in the fall. We finished the LIFU commissioning in January. And we have done this data release of a first exposure just to demonstrate the characteristics of the instrument. And we are actually we started 2 nights ago, what's called the science verification program. So the first slide, there's a nice press release at this link, and I encourage you to go and look for it, where there is a lot more detail. But in addition to the first slide announcement and then beautiful pictures, we released the data to the scientists so they can start playing with it, understanding their characteristics, and why not, giving us feedback on what issues they find in the data. We are now working on the second release, second data reduction that we have done after learning the feedback from the scientists. And what was our target? Well, target is a famous target called Stephan's quintet. And here's a picture of it. Stephan's quintet is not a quintet, it's not a system of 5 galaxies, it's a system of 3 galaxies. But there are another 2 who are along the same line of sight at different distances. So we still call it the Stephan's quintet. And this picture is from Hubble Space Telescope. And this is the 3 main galaxies. Actually, I should say 4, because this galaxy also belongs to the group. But this one is a galaxy that is a lot closer to us, and it does not belong to the group. But then there is this blue arc. This is not a galaxy. This is gas, in intergroup gas that is detected in X-rays, which means that it's very hot. So we have used here HST, Hubble Space Telescope, image of the galaxies, but then we've superimposed image from the Chandra X-ray telescope to show that something is happening, because here there is always this gas that is heated at at temperatures, at a million degree temperatures. Here's a picture, the picture of the first release, the first data release of the James Webb Telescope, which I've used here to show the pointing of the WIF LIFU on top of this system of galaxies. we've targeted these two galaxies, and we're going to get a spatial information, a spectral information on all of these points in the galaxies and the region in between, including part of this arc that is the hot gas. When you take spectra, you get this 570 points, and then you analyze each one of them, each fiber, and then you interpolate and create a map, a grid, a square grid. It was called a data cube, extracted from all of these spectra. And the data cube has two dimensions that are spatial, and the third dimension is spectral. In this case, we cover from 900 angstrom, sorry, from 3,700 angstrom in the near ultraviolet to 900 angstrom, 9,000 angstrom in the near infrared. And to give a flavor of the kind of data that we are obtaining and the richness of the information, we give examples of some of the spectra that you can see extract from different parts of the galaxies. So from the nuclei, you get spectral characteristics typical of all the stars. There's emission of the stars. You have millions, millions, millions of stars emitting light. You get all superimposed, and you get the spectra of the stars broadened by the velocity distribution of the stars along the line of sight. So the astronomers look at this, and they can say right away, just by looking at this spectra, they can say, well, this is a stellar, this is stars that are about 1 giga-year old. So just by seeing that there are some spectral features, but there are some that are not there. So and then you can analyze this with models, with the stellar models, and get a lot more information on the ages and the metallicities of the stars. But then, because you measure the broadening of the spectral lines, you obtained the range of velocity, what's called the velocity dispersion inside of the galaxies. So this is for the stellar parts, which here I've showing two nuclei, the stars from the two nuclei. But then when you go outside and it seems that there is nothing here, there is no stars, you look at it, get a spectrum that is completely different. And it's not an absorption line spectrum, but you see emission. So this is gas, and this emission from the gas that is being excited by something. In this case, with the narrowness of these lines, it means that this excitement is from hot stars, it's from regions of a star formation. So with this, you analyze, you can obtain the properties of the star formation, the kind of the temperature of the stars, etc. So this is a star forming region. Down here is another star forming region. Now here, where I show nitrogen and hydrogen alpha lines and nitrogen, ionized nitrogen lines, here's astronomers will already see right away that something odd is happening here, because the lines are not narrow. They are broad and they are asymmetric. This asymmetry that you see here, and these broad tails, this is indicating that there is very strange motions in this cloud of gas along this line of sight. So this broadening is all Doppler broadening. So this can be analyzed to obtain, to decompose these velocities into different components. This is also examples of line profiles that are very, very complex. And these are all from this region that is emitting X-rays. So it's very hot gas, but possibly also gas at different distances, at different systems of gas. So some may be associated to the galaxy, to one of the galaxies, and others be gas that was intercluster gas before the collision. I haven't mentioned, but these two galaxies show a difference in velocity of 770 kilometers per second. So in the this galaxy is moving towards us. course, this is, sorry, this is a wrong expression. It's not moving towards us because they're all moving away from us because there's expansion of the universe. But the velocity of the more massive galaxy, which is this one, if you look from here, from this galaxy, this one is moving in this direction. That's about 800 kilometers per second. This is a very high velocity for a galaxy collision. It's called an impulsive collision because the gravitational impulse occurs in a short time, and the galaxies have passed one another before the stars have been able to react to the changing gravitational field. So it's an impulse, a very violent impulse, gravitational impulse that is transforming these two galaxies. Regarding going back to WIF, I said that we're producing science-ready data, and here's an example of how we obtained velocities of the internal velocities of the galaxies by fitting stellar models. Here, the black is the spectrum in the region of the spectrum in the region around the hydrogen Balmer, one of the Balmer lines, hydrogen beta, and lines of the magnesium and iron. And the red is a stellar model, a theoretical model of a stellar population. I think this is a demonstration of how amazing stellar population models have become. They really reproduce every single feature of the spectrum of a galaxy. It's really remarkable. I've been told that there's errors here, and by errors is this. So this deviation, how the residual has this feature here, and it has a little feature here. So the experts take this and say, well, I need to improve it. But the data is, and the modeling is very good. The other facility that is important in WIF is a novelty in WIF, is that in addition to resolution 5000, which is already quite high, we have another mode that is resolution 20,000. With resolution 20,000, your velocity resolution is 12 kilometers per second. And here you can see the difference of the same space, the same region of a space modeled, observed in low resolution in green, and then in high resolution in red. The kind of accuracy is the information that you gain will go into high resolution. So the science verification program has started, and this is being observed in Q mode. It's being reduced and it's being given to the scientists. This has just started. So can you observe? Can you use WIF? Yes, you can. WIF is being offered for surveys, for predefined surveys that take 70% of the time, and then 30% is offered in open time to the scientific communities of the Isaac Newton group of telescopes, which is Spain, the UK, the Netherlands. So to observe, you can join the legacy surveys. You approach them, and they will discuss with you, and you'll be probably you'll be welcome to join the surveys if you are from one of the nations of the ING, or you can apply to your own projects through the 3 national tags. Finally, there's a system of applying to telescope time in the Canarian Observatories, which is called the International Time Program, the ITP. That will give you 15 nights in 1 year on every telescope on the mountain. So this is for big collaborations, but it's an opportunity to obtain really good data sets. WIF has been offered for the next semester, 23B, only in the LIFU mode. And we have received, or we have just started to analyze the response to these, the proposals have been submitted, which are, I actually was given the numbers yesterday, and I wanted to mention them here, especially for the benefit of Maria Rosa, who is the chair of the Spanish Time Allocation Committee. We can discuss it afterwards. The surveys, how are we doing with time? Perhaps I should start cutting the talk. I could describe a lot more the surveys, but it's getting a bit late. So perhaps I will just mention that there is a paper out describing accurately the 8 surveys. And it just say that they cover basically all of the science areas in which multi-object spectroscopy can be effectively used. One is called Milky Way archaeology, which you obtain chemical and velocity information for millions of stars in the Milky Way, combined with Gaia, information from the Gaia satellite, and with this you trace the formation history of the galaxy. There are projects on galaxy clusters, on stellar populations of galaxies and intermediate redshifts. Analysis of nearby galaxies combined with neutral-hydrogen maps with the aperitif detector on the Westerbork radio telescope. There's a program to obtain redshifts for low-far sources. Low-far is the acronym for a low-frequency array. It's a low-frequency radio telescope operating on many countries in Europe. And it's going to be detecting sources of star-forming galaxies to very high redshift. But it will not be able to tell you at what redshift the sources are. So we will be measuring the redshift, therefore determining the luminosity, the radial luminosity, and the distance of these galaxies. There's going to be a project on stellar and circumstellar physics, a study of white dwarfs. White dwarfs are stars that are at the end phases of their life, and the surveys started looking at white dwarfs as calibrators, as flux calibrators. And then we've seen that having all of these white dwarfs measured, might as well study them also. So they're going to be used not only as calibrators, but also as sources of information about the white dwarf physics. And finally, a study of QSOs, quasars, to obtain the large scale structure information. So these are 8 surveys that are going to be starting. The LIFU parts are going to be starting in the early summer. The rest will start in October. So this is what I wanted to talk about WIF and the William Herschel telescope. But I also wanted to mention, not much, but to make sure that everybody is aware that a planet hunter, a spectrograph, is being built for the Isaac Newton telescope. The Isaac Newton telescope is a 2.5 meter telescope that we run, and is being now converted, is being robotized, so it will operate robotically. And a spectrograph is being built by a Cambridge group, University of Cambridge, or by a consortium of universities led by the University of Cambridge, led by Didier Queloz. The instrument is a replica of the HARPS spectrograph, very successful spectrograph. Has been finding extrasolar planets from the La Silla 3.6 meter telescope, and later as a second incarnation of that spectrograph from the TNG, the Galileo telescope on La Palma. So ours will be the 3rd HARPS instrument, and correspondingly called HARPS 3. And it's supposed to arrive in late 2024, so in about a year and a half. With this, we will have our two instruments being modernized with completely state-of-the-art instrumentation, one for Milky Way, galaxy, cosmology, the other for extrasolar planets work. And so summary, there's new instrumentation. We will start doing science this summer. Open time observations will be scheduled. Will start in November. We will try to promote the synergies with other facilities, especially in the Gran Tecan telescope, the 10-meter telescope, but also on other large telescopes in Spain and elsewhere, also in space. The MOS mode, I think, is going to be the most competitive, the most powerful. We're talking here big data because it's millions of stellar spectra of all types, carefully selected. So there's a lot of opportunity to do stellar libraries, to learn about stellar evolution, and not only about galaxy archaeology, the history of formation of the Milky Way, but also take all of these stars and analyze them to learn about stellar physics. And the final picture is 1992, William Herschel telescope in a photographic technique in which you do at night, you rotate the dome, and so you take the picture and see the whole inside of the dome as if there was no dome. So this was done in 1992 here with a telescope that is quite bare. And 2023, we repeated this now with WIV on the top, with a WIV spectrograph in one of the Naismith platforms enclosed, and with another enclosure here containing adaptive optic systems. So this is it. Thanks very much. And I'll answer your questions. So.
Thank you, Marc. We will alternate questions here and questions in YouTube if there are questions. Don't be shy, raise your hands, and I will give you the microphone. It has been a very clear presentation, it seems. Izaskun and then Santiago.
Thank you very much for the nice presentation. I probably don't know much about exoplanets, but I was wondering, how does your new instrument compare to Carmenes, for example, regarding the spectral resolution?
I believe the spectral resolution will be higher because HARPS has a resolution of slightly above 100,000. But the main difference is going to be that Carmenes operates in the near infrared. And HARPS is visible. And therefore, I suppose that Carmenes is better suited for low mass stars, which do not emit much light in the optical, but emit a lot of light in the infrared. So I suppose this will be the main difference.
Okay. Thanks. And then I was also wondering, in the image that you showed with the galaxies, the first data release. So you showed one spectra that you said, outside the galaxies interacting, that you said that emission was due to star formation. But does that range cover the H alpha line? Because I didn't see any. I mean, I couldn't see from here very well from the back.
Yeah.
Yeah, the plot on the right, the bottom.
You mean this
that one?
I was describing this one, eh? That's the one.
Yeah.
Yeah. Well, here, this is not H alpha, but this is a very small spectral range, and it's showing H beta and ionized, doubly ionized oxygen. If I would move farther to the red, I would see H alpha. Certainly, yeah.
Okay. So that's how you identify, the star formation, mainly by using the H alpha, I guess.
But I'll use all of them. I'll use H alpha, H beta, oxygen 2, oxygen 3, nitrogen 1, nitrogen 2, and sulfur 2. Next to H alpha, there's lines of nitrogen and lines of sulfur. And there's been a lot of physics done in understanding the characteristics of those lines. And actually, although astronomers tend to like stars and galaxies, things that we believe we can touch, that are solid, although stars are not solid, of course. But really, if you want to do physics in astrophysics, you'll do a lot more physics in the interstellar medium than in the galaxies. You can do a lot more physics. Things work a lot better in the interstellar medium. So all of these lines are very well understood. You can obtain a lot of physical information on those clouds.
Yeah. Yes. Okay, thank you, Marc, for the nice talk. Well, now that we are seeing this spectra, isn't it weird that the nitrogen profiles in the spectra that you are showing there are so different? It's not something that can
it be instrumental? Can be
well, I don't know people that have seen this spectra have interpreted that, but in principle, one should expect the same profile for the.
You should
for the
but you may not. So this is nitrogen.
Yeah.
But you're saying, well, this is nitrogen too, but I don't know what this is.
Yeah. Okay. Yeah. Yes.
I don't know.
Yeah. But in principle, yes, it's interesting. Well, anyway, what I wanted to ask you is if you have any, you can give us some information about the sensitivity limits, especially for the LIFU. Do you have an idea? I mean, how deep can you reach with this mode? And
I'm sorry, but I don't have the number. I've been banging the head of the team of astronomers who have analyzed. The analysis has been done. A typical thing you do, you take nights and nights of data, you analyze it, you take the note in your notebook, and you don't put it on the web page.
Yeah.
And that's the stage. And I still don't have the number.
Okay.
The throughput, how much light you get at the end from what comes in a multi-object spectrograph is mostly affected by the accuracy with which you can position your fiber. Those 20 micron positional error that I mentioned before. So that's the aperture losses. Is your star well-centered or is not well-centered? Here's where you lose all of the light, more than on the fibers, which you also lose some along the fibers. Our understanding is that the throughput numbers are good. We don't see problems there in the transmission of the fibers or in the characteristics, the throughput of the optics of the spectrograph. We do have a problem in one of the chips. In the blue arm, spectrograph has two arms. It separates the light to optimize the optics. So on the blue arm, the camera contains two chips. There's a mosaic of two. And one of these two chips has a read pattern, read noise pattern that is above the specification. We have done a lot of changing of electronics to get rid of it. So far, we've improved it, but we haven't managed to clear it completely. And this is the fundamental limit that we have now. We're still working, we're still planning more upgrades, but we do have an issue with the read noise of one of the detectors.
Okay, thank you.
Maria Rosa.
Thank you. Thank you, Marc, for the presentation. Very, very didactic, very beautiful. I would like that you mention what the plans are for those projects that have one or very few targets, and they are very, very separated in the sky. I know the answer, but I think the audience may have this question. I think it is important that that you inform all of us when you have projects with very few objects in the same field of view. Will you accept these projects can be scheduled together with the big surveys? And the second question is what the plans are for the other instruments that are available on the William Herschel telescope. You didn't mention what plans there are. If there are plans, I guess you already have the answer.
Yes, to answer your first question, we have agreed within ING that we want to maintain the community of astronomers who need single targeted spectroscopy. To date, before WIF, single targeted spectroscopy was done very well at the William Herschel telescope with a spectrograph called ISIS. A very good spectrograph with which many of us have done part of our thesis and our research. Very big discoveries have done with that spectrograph.
Eurofighter. You can.
So we want to continue offering telescope time to those communities. And so what we did is ask ourselves the question, observation that was done with ISIS before, can it be done with WIF? I mean, WIF can observe 900 stars at the same time, but it can observe one star too. So we realized that for us, it's better to give one fiber to an astronomer who needs one fiber, rather than having to take WIF out sometime in the year and bring ISIS into the telescope. So this is an instruction we've given to the time allocation committees. The time allocation committees should not penalize a project because it only asks for one target, because this is a community that we want to retain. So please go ahead and ask for and use WIF for single target. There's several ways in which the other systems, the rest of the fibers can be used for you. Imagine you could have a fantastic measure of the brightness of the sky, because you could have the 900 fibers minus one your target, and all the others on the sky. You can measure the spatial variation of the sky flux if you wanted. You could understand lots of things about your observation. And then the data is reduced for you. So the next week, you get the data completely reduced. So there are advantages of using WIF in single target mode. There's a second part that you didn't mention, but I think it's in your mind, which is, well, if you use one fiber for one target, for one project, could you use other fibers for other projects? And in principle, this is absolutely doable, but we're not going to be offering this for certainly in the first year, and perhaps not the second year. This is basically a bookkeeping issue. Understanding what fibers belong to who will be able to use this data when, this sort of problems. And maintaining the management of this using the SEMSOVA systems that are being produced for using big surveys is not immediate. So this will happen, but will happen in some time in the future. Okay. And then your second question about the other instruments. Well, we are reconsidering the frequency with which we will bring up other instruments. Our advertisement had always been that on a cadence of 9 months, we would take WIF out and bring in the old instruments. We believe now this is not advisable because the instrument change is a lot more complex than we had envisioned. And it's also even takes some risk to the instrument. So for the first year and possibly 2 years, we'll operate with just WIF. And then we'll see what demand there is for the other instruments.
Marc, there is a question in the chat by Rosa González. Congratulations, WIF is wonderful instrument. Do you have last news about the start date for the science verification project with MOS?
The expectation is July. So
okay.
In July, we should be doing science verification of the MOS mode. July, mid-August. Okay. We'll see, of course, we haven't done the commissioning. We haven't completed, we have just started the commissioning of the MOS mode. And I should correct myself, we haven't just started. We started the commissioning of the MOS mode in October. But we gave more preference to completing the LIFU, which was shorter, easier to do. And now we have retaken the MOS commissioning, and we are working hard, overlapping MOS commissioning, LIFU science verification. We're sharing nights, roughly. And the MOS commissioning should be finished in June.
Okay, and then the last question, Miriam.
What an honor. Thank you. So thanks for the talk. For us who have fought with WIFOs at the Herschel, this is WIF is an amazing improvement, and it's great to have you here to answer our questions. So the first one, I should know the answer, but I forgot. WIF is not adaptive optic assisted, is it?
No.
Okay. Yeah, because I always have the complaint of why are we seeing limited with a fiber head entrance for us who work on isolated stars in farther systems. This is a problem, but of course we will adapt somehow. The second question I had is how do you manage the fibers to cross in the focal plane? Is because there are 2 layers of fibers, or do they have capabilities of moving in the y-axis?
Well, there are 3 layers of fibers. Fibers are parked around in a circle, what our British PI calls a bull ring structure. So there are 3 layers, and so the robot needs to know the exact height of each of the fibers in each of the 3 layers. So all this is all tabulated, and the robot grabs it and places it. And yeah, the ones from the first layer go below, the ones from the top cross over.
And how close can the fibers be on the sky? Because that was a problem with WIFOs, but I'm sure.
I believe that the nominal value of the proximity, the maximum proximity, is slightly worse than AF2,
okay, because
the buttons are slightly bigger.
Yeah, but then of course you can cross
yes.
and use another layer. So
yeah, it's basically you need a given size of the magnet. Each button has this magnet that keeps the fiber there at the position where you left it. And this magnet needs a given size in order to have sufficient force, magnetic force to maintain the button there. We're having the fiber pulling because there's a spring pulling always, trying to recover the fiber back. So that the button is slightly bigger, I believe, is slightly bigger than our predecessor AF2, and therefore the separation, the minimum separation is slightly bigger.
If well,
in 9 seconds. In arc seconds, they are
No,
asking?
I don't have the number on the tip of my tongue. I'm
But
sorry.
it could be something like 3-4 arc seconds or more.
No. It's more like 40 arc seconds.
40.
40, yes.
Wow. Okay.
Yeah.
Okay. One very last.
For AF2, they said that the minimum distance was 30 arc seconds. Yeah.
And if I can ask the very last question, so
sure. You should be able to ask. You are a predecessor of WIF here. So yes.
So I was actually going to ask about the INT, which is a telescope that a lot of us have used to learn actually. I was wondering if it's going to be dedicated exclusively to HARPS 3, or is any imaging instrument like the wide field camera going to be operative, or just HARPS?
The wide field camera will not be usable. The agreement with the consortium is that the consortium takes 50%. In practice, will be close to 60% of the nights, but that's not complete nights. It's of every night, because their survey is just one experiment that takes 10 years, obtaining spectral information every 24 hours for a group or a few stars. So we will not be able to mount the wide field camera. We'll keep it. So if they would have to repair the instrument for 6 months or so, we could mount the wide field camera. But otherwise, the wide field camera will not be usable. Now, there's an opportunity to mount a second instrument in the folded Cassegrain port of the INT. We will consider that possibility depending on demand from the astronomers. And we have the instrument already, because the instrument is ACAM. So ACAM on the Herschel can be mounted on the folded Cassegrain of the INT. And that's something that may be considered if there is demand.
Good. It's over. We thank Marc again, and let's go for lunch.